our very own Kishor Bharti. So he's a senior scientist at A-Star, and prior to that, he was a postdoc in University of Maryland in the U.S. And before that, he did a PhD in CQT. So yeah, today's going to talk about this multivariate bicycle code, which is this generalization of this bicycle code from this paper, a Nature paper by Bravi et al. So yeah, stage is yours, Kishore.
Yeah, thanks, Andrew. So thanks a lot. Yeah, so let's start this. So it's called multivariate bicycle code, and yeah, so I just prepare it, like in Mutability, and so you can see here is the abstract, and here basically we introduce this thing called multivariate bicycle codes. So we have a multivariate bicycle quantum LDPC codes. And this you can think of as a generalization of bivariate bicycle code. So there was this paper in Nature by Bravi et al. And that was basically bivariate bicycle, bivariate bicycle. So these codes, they had, the weight of the operators, which you perform to, get information about what errors have occurred. The weight is 6 there. So what do we mean by weight of an operator? So let's say if I have an operator like X, Z, I, Z, the weight is basically number of non-identity polys in the operator. So for example, here, the weight is 3 because number of non-identity polys is basically 3. So that's called the weight of the operator. Now, if the weight of the operator is large, if you want to, experimentally implement it, it will be challenging. So you want smaller weight operator. So in this Nature paper, the weight of the operator, which I mean the codes that they have, the corresponding, the measurement that they need to perform, the weight was 6. So what we do is that we generalize. First thing is that we generalize bivariate to multivariate. And we also propose a smaller weight alternatives. So we have weight 4 codes and weight 5 codes. On top of that, these codes, they have, similar to the IBA paper, some of the nice structure is imported. So for example, it can be implemented in a double planar structure. So, like this is a biplanar structure. So qubits can be arranged like this, and then you just need to connect, and maybe some of them you need to connect to the third dimension, and so on. So that is good. Maybe if you can use extra dimension, maybe you can implement this quantum LDPC codes, because these codes, I will talk about what this low density parity check code means, but they require long range connectivity, and often you can you can have long range connectivity uh, uh, by using these extra dimension like the third dimension. So the biplanar structure is nice. We also show it has some kind of a toric layout, and what we show that our encoding rate is comparable to the it's better actually, with comparable encoding rate, it has a better performance than corresponding surface codes. On top of that, we show that, for example, we have codes where we can encode 4 logical qubits with distance 5 into 30 physical qubits. So you see that just using 30 physical qubit, you can have 4 logical qubit and distance can be 5. So, that is maybe okay. On the other hand, if you want, similar uh, uh, performance, you need around 100 physical qubits. Okay. So this work was basically done together with, so it's like the first person is Lucas here, the second person is Sim, and third person is Toby. And yeah, like this is. So
Kishore,
and in the paper,
Kishore,
yeah, yeah.
what are bivariate bicycle codes? Can you elaborate on that,
I,
please?
I will explain. I will explain. Yeah, yeah, yeah. Just giving like high level summary. So it's more like I will come to that. I will spend some good amount of time like on this paper where the bivariate bicycle code was introduced. Yeah.
Okay, thanks. Yeah.
Yeah. So this is a paper by like Brabby Cross and like Patrick Roll, Gambetta, Maslow, and Yoder, where like they introduced this bivariate bicycle codes, BB codes. Okay, so that is nice. So let's look at the abstract of like this paper, not our paper. Like our paper abstract we just went through, but let's look at the abstract of this paper. So in their paper, they propose very nice codes, and like they they can preserve it for a long time, and everything was very good, like and the and the kind of codes that they looked at was uh, went beyond regular surface code, and basically the codes that they were looking at is is quantum analog of something called LDPC codes. So I will explain what is an LDPC code, what is a bivariate bicycle code, and then set the stage for like our discussion yeah. So in LDPC codes basically, which means low density parity check codes, the number of bits involved in each check and the number of checks acting on each bit both are bound by a constant for all members of the code family. So every bit participate in some constant number of checks, and every check acts on constant number of bits. If that happens, then like you call your code as LDPC code. Uh, in terms of parity check matrix, you can think of like that it's basically the sparsity is constant. And actually like many modern technologies such as Wi-Fi, 5G, and so on, like they are error corrected using LDPC codes. So LDPC codes are very nice. And here comes like this very beautiful paper by Daniel Gottsman, who is like one of our heroes in quantum error correction. And he basically like he suggests that we can do fault tolerant quantum computation with constant overhead using quantum low density parity check codes. So like we can have the quantum analog of these LVPC codes, and using that like we can do like with constant overhead we can do fault tolerant QC. So in quantum case, like what is a notion of LDPC code like that one can think of. So there is this definition which I have borrowed from like this paper by Daniel Gottsman. So let's say you have an n-k stabilizer code. So let's say if you have like k qubit of information encode in like n qubit, such a stabilizer code you call it RC LDPC code. If there exists a choice of generators for the stabilizer Q of the code, such that the weight of each of the like generator is upper bounded by R, and the number of generator which act non-trivially on qubit J is at most C for some J in 1 to N. So there are two parameters. We said the weight of the each of generator is R, and C, like it's basically number of generator which act non-trivially on a particular qubit. I mean, for all qubit, like So there are two parameter R and C, which one tells like what is the weight of the check. The other tells you how many mm, checks participate in a qubit, and given a qubit, how many checks act on it, and given a check, how many qubit it acts on. So like there are these two parameters R and C. And ideally, I mean, if you think about all codes are LDPC codes, just that the R and C parameters are like large. But ideally, you would want your R and C to be, like some constant. So that's what people, like mean when they normally talk about LDPC codes. So for quantum LDPC code, there is very nice survey by Brookman and Everhart, which you can look at. And there, basically, they, like they talk about all of these nice codes, like uh, and different kind of, like surface codes. Sorry, different kind of LDPC codes. And you have corresponding K and D. And still, like this was not enough, because I mean, like there is this notion of something called good LDPC codes, like good. So they are not good enough in the sense that you want your K to by like N to be some constant. So the constant encoding rate, and like and the distance also, like you would like to uh, basically like a scale linearly with N. So d by N also you want it to like some constant. Yeah, let's call it C1 and C2. And this was solved later. Actually, there are like 3 papers now. I think I need to 3 or 4. Like I need to add more things here. So there was the first paper was like used by given by this Pantalev and Kalachev, who who managed to get like asymptotically good quantum LDPC codes. And these codes, like were later used by like Anshu, Brookman, and Nirket to solve some important problem related to quantum PCP conjecture. Like so it's called something called NLTS conjecture that they proved is correct. And so you can see like how powerful some of these quantum error correction results are. Like you can like you can use it in diverse fields and Maria. So this paper, like by Braby and others was not about, because these codes that we talked about, they're asymptotically good. But often you would want, like the codes, like, concrete instances. And maybe you would like to have, like, yeah, uh, yeah, you would like to have a like nice encoding rate, and you would like to have like nice distance, threshold, and so on. So there were a bunch of codes which was, like proposed here in this paper. And you see that, like, and they also did, like circuit level simulations, and they could, like find that these codes, like, they reduce the overhead required for fault tolerance. I mean, not fault tolerance actually. Yeah, they were not doing processing, but just let's say, like building a good memory by, like order of 10. Yeah. Yeah. By yeah, like so uh, yeah, so this was good. Yeah. So let's look at, like the LDPC codes that they proposed in their paper. Okay.
Sorry,
So
Kishore. So
yeah.
are this from the Pantalev and Kalachev paper, or
No,
is it?
no. So this paper was, about asymptotically good LDPC codes. But
Okay.
so like basically asymptotically good, like they are good when you like reach to the asymptote. But like who goes to that? Like when we are talking about concrete instances, we want a nice encoding rate and distance. So that's where like like the paper by Braby et al. Comes. So this paper said that like you can have very nice codes which are asymptotically good, but maybe like you want to design a quantum LDPC codes which has like I don't know like 200 physical qubits, and you want to have large number of like logical qubits. You want to have like large distance, and then I don't know whether anybody has explored it. I was once having a chat with Bravi, and he thinks that maybe hypergraph product codes could be nice. But I think these asymptotically good codes, like they are constant sitting there, right? Like let's say when you say that k by n is some constant c1, you would like to have this constant, like as high as possible, right? I mean, and let's say that this constant is very small. So maybe when n becomes very large, it's okay. But like for a small n, for concrete instances, like it's not such a good news.
Okay.
So what they did is that actually, like Brabi et al., they took some earlier paper by like Pryadko and Kovalev and Pryadko, and they modified it. So I will talk about the modification. And they introduced this new family of codes called bivariate bicycle codes. So and and for this I mean, and these codes are not like good LTPC codes, but the codes have like also like what you want is that the syndrome measurement circuit should be like small depth. Your decoding should be fast. Like your encoding rate should be like high. Distance should be maybe, I don't know, 40 or 50. I mean, like let's say once we reach there, maybe things will not be like will be fine. So effectively, there are bunch of criteria that you want to satisfy, and then on top of that you want to do some processing on using these codes. So you want to like use it for implementing your like logical gates, so this paper, like the paper by uh, Bravi, like and others, like that they do not talk about processing, that they leave as open question. But what they do is that they build a memory, and for that they propose this bivariate bicycle code, which are not good LTPC codes, but has nice parameters. But it will be definitely like nicer to have, I don't know whether one could explore some of these codes and find concrete instances. Like there are these constants hiding there, right? I mean, you would like to have like maybe you might want to have better parameters than Brabi et al. Yeah. Does that answer, Andrew?
Yeah, sounds good.
Yeah, perfect. Yeah. So so that was good. Yeah, okay. So they came up with this code, which like which has very nice parameters. So this is all very nice. So how do they like prepare such a code? So it's a it's a this kind of codes, like it's a family of codes called CSS codes, which I think like I mean you can find it in Nielsen and Chuang. So basically there are two parity check matrices, Hx and Hz, and they satisfy this condition, Hx Hz transpose equal to 0. And what they do is that they build this matrix Hx and Hz using two matrices A and B. So you have a matrix A and you have a matrix B. And matrix A is basically sum of three terms, A1, A2, A3. And B is sum of three terms, B1, B2, B3. Okay. And then Hx is nothing but A concatenated B. And Hz is B transpose A transpose. So now, if you do Hx Hz transpose, that will be basically AB plus BA. And if A and B commute, so let's say if AB commute, so this will imply 2AB, which is equal to 0 if you are working in F2, right? So that will satisfy the CSS condition. So you just need to find A and B matrices which satisfy this commutation relation. And how do they build this A and B matrices? So A and B matrices, they are built using like certain like polynomials. So A and B are basically polynomials in X and Y, where X is like some shift tensor identity, Y is some identity tensor shift, where like this is like two-dimensional shift, this is three-dimensional shift. So you can have different choice of polynomials. So let's say, and there are like three terms in the polynomial, and given a polynomial, you will get a matrix A. And actually, like I will talk later, like you can always get like these matrices, they will be circulant. And if the matrices if there are two circulant matrices, they always commute. So starting with the shift matrices, if you build a polynomial, like you can actually, like there is a nice, like connect isomorphism with, like polynomial ring of circulant matrices. So if A and B commute, like Hx Hz transpose will be equal to 0. So that was nice. So from there, this condition is satisfied, hx hz transpose equal to 0. And now there is a nice lemma that they provide, is that in terms of this L and M, you can tell how many physical qubit you will require. In terms of just this A and B, you can tell what will be the number of logical qubits you will have. And then you can also, in terms of hx and hz, you can calculate what will be the distance. Okay. So you just need to come up with a nice polynomial, and the polynomial will tell you n, k, and d. That's it. So they come up with a choice of some polynomials. And for those polynomials, they calculate n, k, d, and so on. And that was nice. But all of here you see that, the number of terms is basically 3 plus 3, 6. And that controls the sparsity of your parity check matrix hx and hz. So the weight, basically all codes have weight 6 here. And that has very much to do with, how many terms you have there. Also the polynomials, there's a lot of room there that you can explore. Maybe you can have a smaller number of terms in the polynomial and all that. And there is a lot of room there that you can explore. So then, the question that, one can ask from here, should one optimize for n, k, and d? And maybe one should reduce the weight of the check operators. And there are different strategies that you can take. So this paper, at this point, I would just like to mention that, there is one approach which one can use to reduce the weight of the check, which was in, we had in one of the paper where, using flocate, flocate codes, so we had this hyperbolic flocate code where, you can have, the weight of the check can be reduced to 2. And it's not that, we are not talking in conjunction with bivalent bicycle code, but I'm saying that you can have these codes where the weight is 2, and also the encoding rate can be quite high. Yeah. Okay. So that being said, let's now come to, our work. So I will give a summary of it, and some plots and so on. But before I move there, if you have any question, let's say if something is not clear, maybe you could ask, so that, we can chat a bit. Maybe I don't know, but at least this will lead to some nice research problem or something. Yeah. Okay, I think somebody has some question. If you have a question, please just unmute yourself and ask it.
Hi, how's it going? Thank you for the talk so far. One question that I have is there's still no intuition about how we should choose the polynomials, the exponents, and how do we build the structure of this thing. So we understand that as a whole the recipe works, but it's still we still have is there an understanding to be gained? Is it purely an optimization thing that we'll never understand this deeply because it's too complex, or what's your take on that?
No, that's a very beautiful question. So yeah, in that paper, they use just heuristics, and even in our paper, we did lots of heuristics, I would say. But then there is a work we are at the moment carrying on, with a master student, where we are, trying to look at the code space, structure in the code space when you have a choice of a particular polynomial. So a choice of a particular polynomial, affects how the code space looks like. So at the moment, this is not very much understood. Like when you select a particular polynomial, how, which, what are the symmetries there and so on. I think a rigorous study is required. We have some intuition, but, it's a work in progress at the moment. Yeah, it's not, I think in anything that is out in the literature, nobody has looked at it rigorously. I think somebody else also has a question.
Hi, Kishore. I just had a question about the number of terms in the polynomial and the weight. So you mentioned that the weight of the stabilizers is given by the number of terms you put in these polynomials. So is this like a
Yes,
economic
yes.
position?
Yeah. So I mean, at least the way it is constructed here, what happened that, like so let's say the X matrix is, so let's say in every row, you have just one and everything else is 0, right? And when you do tensor identity, still you will have like similar structure. Now, what happens that the weight will correspond to sparsity. I think somehow it's I am hearing echo. Like, I mean, maybe Navneet, if you could mute yourself. Yeah, sorry. So let's say if like, I mean, if you write these polynomials, what will happen that, like the A matrix that will have the number of places where you will have 1 will be exactly, let's say 3. If there are like 3 terms, let's say it will look something like this. And then what you do that you do A concatenated B. So you will have 3 ones coming from A, and you will have 3 ones coming from B. So the total number of ones will be 6. And let's say if you look at your parity check matrix, like the number of ones that you have, that will determine, like the corresponding stabilizer. I mean, the non-identity stabilizer, right? And the weight of an operator is basically the total number of non-identity polys that you have in a particular stabilizer. So if something like P tensor I, let's say P1, let's say call it like Z tensor I, tensor X, tensor Y. Basically, its weight is 3, right? I mean, so here the number of such one that you will have, like basically 3 will come from A, 3 will come from B. So like total number of ones in your HX matrix will be 6. So that will control, like the weight of the stabilizer. I mean, the check operator that you will measure. Does that answer, Navneet?
Yes, thank you very much.
Okay. Okay. So let's now move to yeah. Mhm.
Can I ask a really quick follow-up question on this?
Sure.
Something that I did not understand from the paper from Bravi et al. Is why did they pick this precise structure such that they have weight 6 stabilizers? So why only 3 terms? They kind of say that they're gonna do that, but they never elaborate on why precisely that and not something slightly different. Is that understood?
I had asked Bravi this question. So he said that if he tried 4, so he tried 4, and in case of 4, they don't get anything interesting like the Tory code, and yeah, maybe he didn't do exhaustive check. So he tried, and 7 he didn't want. So I think it's like he tried 6 and he was getting some nice, like already. Yeah. So in 4 you don't get much interesting thing happening, and 5 he did not explore much, like in detail, and 6 basically he tried and like yeah, and they tried and yeah, I mean this was just one in the first paper, right? So they just tried 6 and they got it. Yeah, but I mean, they could have very well tried 4 and 5 and other possibilities. Yeah. Also, you see, right? I mean, the number of polynomials is humongous. So like there is question about structure. Unless one understands that, like systematically exploring becomes like very difficult. Does that answer?
Yeah, absolutely. I mean, I guess this, as you say, there's no particular strict answer to this because of how complex it is. So maybe them just choosing this one because it works, it's fine. I was just wondering if there is something particularly deeper of it. But that's okay. Yeah. Thank you very much.
Yeah. Okay. Perfect. Yeah. Okay. So basically what we have, like this HX, AB, HZ is B transpose, A transpose. And then HX, HZ transpose, like 2AB, whatever. So Yeah, actually, I wanted to add one screenshot here, but I forgot. Oh, yeah, there's a very nice summary of all this connection of all this between, like a ring of circulant matrices in a paper by Pantalev and Kalachev, another paper where they introduced the BPOSD decoder. So let's say, like it's, I mean, at this point, it's about ansatz. So you can come up with, like a nice choice of A and B such that they commute. And one choice of A and B that can commute is, for example, like the circulant matrices. So circulant matrices commute. Now, the circulant matrices, you can, like they have this property, right? I mean, if you take some particular power after which, like they will become identity. So you can map circulant matrices to something called, like polynomial ring. And in particular, you can look at, like this thing called quotient ring, where, like you have this polynomials, but in the polynomial, you have this property that the moment, let's say, if you raise the variable x1 to L1, it becomes identity. You raise x2 to L2, it becomes identity, like 1, x1, like, and so on, like something like that, yeah. So basically, you can select your x. So, like alternate way to look at, like this paper by Braby and others is that they are, like they are looking at, like R2, this quotient ring, like with just two variables. And they are selecting the choice of variable as, like shift tensor identity x1. And let's say x2 is identity tensor shift. Or maybe, like let me write it like x1 is, let's say, I tensor shift, x2 is shift tensor I. But like, I mean, you can have a general encoding, right? I mean, you can have an encoding where, like I can define many of these tensor products, right? So I could have something like x1 equal to, yeah, I mean, it's a very simple idea, like, I mean, and that's what we explore and, like work around that and prove some things and run numerics and so on. But the idea is very simple. So you just, like look at this quotient ring, and you can, for example, you can define your variable x1 as, let's say, shift tensor identity, x2 as, let's say, identity tensor shift, and x3 as, let's say, shift tensor shift. I mean, more, and then, like you can similarly like look at NKD, which, like satisfy this condition and try to find, like for different polynomials with more variables, whether they give you nice parameter or not, whether they have nice, like implementation or not. I mean, you can in general talk about, like let's say R different variables, where let's say what you do that, let's say you have any, let's say R is, for example, I don't know, 8. So then that means you can have term something like 0, 0, 0. You can do binary, like something, like one hot encoding, let's say, for example, or binary encoding, something similar to that you could do, like 0, 0, 0, 1, like 0, 0, 1, 0, 0, 0, 1, 1, and so on, like 0, 1, 0, 0. And wherever you have, like 1, you put their shift matrix, and wherever you have 0, you put that identity. So this will be something like identity, tensor, identity, tensor, identity, tensor, shift. This will be something like, identity, tensor, identity, tensor, shift, tensor, identity, and so on, like, so in this way, like you can define your variables, and because, like these variables, the moment you take certain power, the shift matrices, they will come back to identity. So, like, I mean, they will satisfy, like these conditions that you have here. So the idea is that, like by selecting different polynomials from this quotient ring, you can select different choice of, like circulant matrices A and B, which give you, like we satisfy the CSS condition, which gives you, the HX matrix and HZ matrix. So this is the, like the key takeaway. The rest is, like, I mean, if you understand this, the rest is, like just, yeah, I mean, manipulations around that. So the whatever we prove or whatever we numerically do and all that, like, and yeah, you would like to have, like, smaller number of terms, like not, let's say in your polynomial, the number of terms that you have, you would like to have that as small as possible. So that will control the weight. So you would like to have smaller weight, and maybe using more variables, you would like to explore a bigger set, and that can give you maybe, like more compact code, for example. So does this, like, make sense? I mean, like, if not, maybe somebody could ask question, because this is the main takeaway. Like the rest is, like, just details, like, around this. Okay. So seems there is no question. So like, let's move further. So yeah, I mean, we run lots of numerics, like lots of numerics we run, and like, let's say for, yeah, we had these more variables, right? I mean, so like, they were looking at just 2 variables, and we look at more variables. So we could find, let's say, examples of weight 4 QLDP codes, PC codes also, which were better than, let's say, Tori code, corresponding Tori code. Some weight 5 codes also we could get, some weight 6 code also we will get, some weight 7 code also we could get, some properties and so on. So I will not go into everything. Maybe I will just look at, like some selected ones and all, and maybe, like talk a bit about that. And I think, and we proved some, like some propositions about, like whether they can be still implemented in a biplanar structure or not, or like whether they have a toric layout or not, and so on. So if you have any question, like maybe please ask.
Yeah, Kishore, I'm just wondering. So how essential it is to construct this X and Y and Z using cyclic matrices? Can we just
not you see that, I mean, so you already got it, Andrew, right? I mean, it's about, you have to satisfy this HX HZ transpose equal to 0.
Yes, yeah.
And to satisfy that, what you need is that A and B, they should be circular matrices.
So that is sufficient, but not necessary, right? There.
Yeah. Not necessary. Not necessary. Exactly.
Okay.
Yeah, you're pointing to the right thing. Yeah. So you see that, like what you need is that, HX HZ transpose equal to 0, and if they are circular matrices, or let's say if they commute, then you get 0. But like, I mean, it's not needed. Yeah.
Yeah. Okay.
I mean, it's not like, it's not necessary. Yeah.
Interesting. Thanks.
Yeah. So yeah, you see, right? I mean, already there is, like, I mean, I think it's, I mean, this paper, I mean, the Multivariate Bicycle code, or all of this code is about choice of ansatz, one would say. Like, I mean, can you have better choice? I mean, circular matrices just give you one choice of ansatz, but they are not the only one. You could have something else also. And maybe A and B does not commute, but still maybe, I mean, I don't know. Somehow you can have, yeah, like, I mean, maybe it's not necessary. Maybe it's just sufficient. Sufficient we can see easily, right? I mean, it's sufficient, yeah. But maybe it's not necessary. Yeah. So you see that, like, I mean, so for example, like, there are certain codes, like, we just mentioned here, like the corresponding. So we just take, like some candidates from weight 4, weight 5, weight 6, weight 7. In particular, look at our this code, 34.5 code. And we compared it against, like a code, yeah. So this is our different codes, like weight 4, 5, and so on. And, like, look at, like how does the physical error rate and the logical error rate behave and so on at different error rates. There are some statements about, I just put one statement about implementability and so on we proved. So yeah, I mean, yeah, I mean, so you can find actually this biplanar decomposition in linear time, and And if certain conditions are satisfied, then you get biplanar architecture. So all our codes have biplanar architecture. Yeah. Like this is a picture about, like how the corresponding Tanner graph will look like, and the connectivity. Here I have, like I only shown the non-local connections, like in this figure.
Sorry, Kishor, can I
Here
interrupt
is
you for a second?
yeah.
I wanted to ask about this biplanarity property, because
Yeah.
if you define some Tanner graph to have thickness 2, that doesn't mean it's 3D local, right? That just means that it has thickness 2 means that I can arrange my edges in 2 planes, right?
Yes.
But even if let's say my piece of hardware had precisely 2 layers, does this imply 3D localness? Do I have a quantum tangle that's like local in 3D?
Yeah, I mean it will very much depend. It will depend on, like let's say, the only means that you can arrange in 2 layer, but like it depends on, like the qubits that interact, how they are positioned there, right?
I
I
agree
mean,
that
yeah.
I was gonna say I feel like I definitely, my intuition is that I agree with you that it's not necessarily 3D local, and as a result, I fail to see a bit more than why is it interesting that that it has this biplanarity property, because it might make things slightly simpler, that you can argue in favor of that, and maybe now I'm thinking in terms of implementation, right? It might make things a little bit easier, but it's still pretty complicated.
Yeah. I mean, so like I think we have this this how the Tanner graph looks like and all, but in 3D, like let's say when you put it, let's say you assume all-to-all connectivity. I mean, put it in let's say in qubit case, maybe. Maybe no, you can't assume all-to-all connectivity. But maybe you just, like you have a particular topology, it will depend on the topology. So let's say a square connectivity, and then you have another square connectivity on top. I think one has to see whether you can position, like, so here, for example, like for the x checks, the interaction vector is like -4, -3. So let's say, yeah, I mean, you can see that this one is connected to this one, where, like you go like 1, 2, 3, and then 1, 2, 3, 4. Now, let's say I don't know whether I can position it in 3D such that, yeah, still looks, I mean, I don't know, maybe it will look distorted and so on. I mean, we did it because, like the IBM paper also did it something. So, like we just proved some stuff, but I agree. I think, like one has to check, like uh, among all codes and see. I mean, it's better than, let's say, so certain cases, like that you may not even have the biplanar structure. So that's bad. So biplanar structure, you get some hope, but on top of that, I very much agree with you that one has to go into, like more details and see whether it will correspond to also 3D local. So I think that's another implementation challenge you are asking for, maybe. Like does that answer, or maybe, or do I understand your question properly?
Yes. I guess yes. Then maybe the last point is like, is it clear that whenever it's not biplanar, it's going to be bad? Is it?
So let's say it's LDPC, right? So it means that, like one, I mean, so to beat surface codes, you need to have non-local checks. And
Sure.
let's say, if the qubits with which you are interacting, they are very far away. So it will be difficult to, like either you can apply some kind of swap gate and make them talk to each other, which is, I mean, which can be bad in, like because it can induce noise and all. Other thing is that you use this biplanar structure. So, like you use 3D to, like make them local. But then, like the issue that you ask it in 3D, maybe also, like the qubit with which it interacts, maybe it's still far away. I mean, it could very much happen. I don't know whether IBM paper looked at it. We did not look at this thing exactly. So yeah, I think yeah, I think it will be worth looking. But let's say instead of biplanarity, you get triplanarity. That's even bad, right? Let's say you get three planes now, in which like, I mean, so anything beyond 2, that will be bad, right?
Yeah. No, I guess I agree. I was wondering if if there is any argument in terms of maybe you don't have biplanarity, you have something slightly higher, but it's still okay for some other different reason. But I guess
maybe I don't know. Maybe it could be something like this. Like you have something above, something below, like triplanarity, and maybe like you. And in that case, you have local. Yeah, I mean, one could imagine such scenarios. Maybe, yeah.
Yeah. Okay. Thank you.
Yeah. Yeah. So, and then there was this, like one of the 6428, it looks like kind of a twisted Tory code, like when, like it's yeah. So I just put it here because the figure looks nice. Yeah. We also compared it, like against, let's say, some of the codes, like Maryland has this weight 6 code, like 7286 code. So their weight was 6. IBM also had weight 6. Our code, on the other hand, has weight 5. And then if you look at, like the distance is also comparable. And that's why you see that, the error plot is like, almost similar. So like, so they get distance 6 at 72. We get distance 6, like, I mean, with low weight at, like with just 30 qubits. So like distance 5. I would say compared to Maryland, our encoding rate is better, but compared to IBM, our encoding rate is worse. Like, so this is, but yeah, like the weight is a small. So this is a small code, like one could possibly, let's say, like try experimentally implementing, like check, like what exactly it corresponds to. Like, I mean, let's say in terms of, like the 3D local structure and so on. Yeah. Okay. And then, yeah, I think that's it. And then we had a bunch of more plots, but like these are details you can look in the paper. So I think that's all. I think all the major points, like they are covered. And there are some details about, like, well, like when can you have toric structure, when can you have biplanarity, which conditions need to be satisfied. I mean, all these things, like we have listed on in the appendix. So in the appendix, you can see, like, I mean, there are some more rigorous proof for all that. And also in the main text also we have, like a section on implementation. And yeah, but those are, like, I mean, details around all this. I mean, so this was all the, I would say, message that I wanted to convey. Uh, uh, if you have any question, please ask. Or, like, I mean, I think I have done otherwise. Yeah. Yes, I think people have question. Like, just unmute yourself and ask maybe. Yeah.
Thanks, Kishore, for the talk. I wanted to get your comments on. So you mentioned that these codes are still not good LDPC codes, right? So is there some hope for some variant of this line of research to result in good LDPC codes too?
Yeah. So I think, like maybe like one could take this good LDPC codes, like which, I mean, there are 3 of them, I believe, or maybe more, which have been proposed, and then try to, like look for like concrete instances there and see, like what needs to be tuned such that, like you can beat, for example, this bivariate or multivariate bicycle codes. Yeah. In terms of encoding rate, distance, and so on. Yeah. But yeah, I think this is all open. Like, I mean, IBM basically in certain sense started this direction. Like, I mean, in certain sense, like, I mean, like, but there is hypergraph product because the paper they selected and they improved upon is by Kovalev and Pryatko from 2013. But then after, there is this many nice codes which have been proposed, and like, and forget the good LDPC codes. Like, I mean, even there are, like many of these other codes which are, like, I mean, which are there. And one could, like one could take this good LDPC code, but there are other codes also, and one could try to optimize the constants and find because these are good, like, I mean, they are computer science wise nice, but I would say when, let's say, when people have implementation questions and all, and like when we are doing, like, we are talking about device and so on, like, when I think the particular constants become very important there. Yeah.
And can I ask you, like, where in this table do these BB codes or multivariate codes fit? Like, what would be the asymptotics?
Oh, asymptotics. I don't know. It's very heuristic, right? You see that it's in terms of this. Oh, yeah, because it's in terms of the this parity check matrices, which depends on the polynomial, and ultimately it relates to, like, I mean, asymptotically, like, given some polynomial, what is the best encoding rate asymptotically you get and all. I don't think like it was not in the IBM paper, and I haven't seen any paper which has, like, I mean, studied this in detail. I think this is a important question, research question, maybe I would say. Yeah.
Got it. Thank you.
Yeah.
Yeah, thank you very much. I still have a few questions because I think this is a very exciting topic. Maybe one practical question, I guess, on these results is that do you have a generic recipe for the syndrome extraction circuit, or did you heuristically find it for each one of the cases? Is there a particular circuit recipe to obtain, to measure the syndromes? I'm thinking of building the circuit for any generic polynomial that you have. In the IBM paper, they have a generic one that works for whenever you have 3 terms in your polynomials. So I was wondering if now when you add more terms or a third variable.
I think we did not look at that here.
But here you had to simulate it through a circuit, right?
Yeah, no, it was not circuit level. Yeah, it was not circuit level, like noise. But yeah, I think, like, maybe you're asking for, like, simulation at circuit level noise, which I believe
Yes.
is nowadays the standard. Like, I mean, I did it very, like, old school. Like, I mean, like we did it very much old school. Like by just taking the parity check matrices and then, like, fitting it through the pancake. Like pancake has a nice library, and then, like, using it. But I think ideally one would like to fit it through some Steam or some other package. And
Yes.
yeah, so I think we were not. I mean, we were mostly approaching it, from the perspective of giving better codes and all of that. But I think this implementation question, like, exactly it has not been touched in our paper. Like where like you go at the circuit level and like yeah, like try to see how to, like, I mean, yeah, I don't know. Yeah, I don't know. Yeah. I mean, we could talk about it if you're interested and all. We could have some meeting with, like other people like Toby maybe. Yeah. And
Yeah,
or,
that'd be great.
or
That'd be great.
Lucas and yeah, I think. Yeah, I mean, I think these are all research questions and all, like that you guys are asking and so on. And I mean, I would say the research on this topic has very much, like, started, and and uh, um, and there is a lot to be done. So, for example, the question that Andrew was asking about, like, I mean, the choice of others kind of answers, or, like, I mean, the implementation things like, 3D locality, like the structure of the code space, like, how does it relate with polynomial, that we are very much looking at the moment with someone. But in general, there are many of these questions which are open, and people are interested or whatever. We could chat in Discord and so on, and, like, I mean, see where things go. Yeah.
Awesome. I have maybe one other question about the structure of the polynomials, or whether
Yeah.
there's an intuition on what would be better for logical operations. Is there, do we understand, or has anyone explored the carryover of this?
No. I think, like, I mean, I think IBM paper also doesn't look at even the bivariate cases. But I think there was a paper that came later, like I think last month or something, from IQM or some place, and they
Yes,
talked
yes,
about
yes.
some symmetries or something.
Yes,
Yeah.
I've not gone through this one either, but I know there's the existence of
Yeah,
that
yeah,
one.
yeah, 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 yeah. So I think that may have some answer to your question. Yeah. But one is to do the same for our multivariate case. Yeah. Or let's say, general case or whatever, like even understand there and so on. Like even there was, I think there was a talk by Chian recently. About because they are in this LDPC course, one of the issues is that like they are not the logical operations are not parallelizable. Like they implement them in serial, and he used this for homological codes, but somehow the same techniques like do not seem to work for bivariate bicycle codes. So these codes like somehow have different structure and all, and I think one has to understand it in detail. Maybe the IQM paper has some answer. Yeah.
Okay. Thanks. Yeah, okay. I think that was all my questions. Thank you very much.
Yeah. Thanks a lot. Yeah. What's your full name? Like, I can only see EZE. Yeah.
Yeah, it's Eze. It's Ezekiel.
Eze.
Yeah, I'm one of
Okay,
the
okay.
researchers at Entropica Labs.
Oh, okay. I think on in LinkedIn, I think we had some chat, right? I think some point. Yeah.
Yeah.
Ah, very nice. Yeah. Yeah. Let's chat sometime. Like we could meet in A-Star or CQT or Entropica or someplace. Yeah.
Right. So, yeah, if there's no more question, then I guess yeah we can wrap this up. And again, thank Kishore for the nice talk.
Thanks, Andrew, and thanks everyone for the nice question. Yeah.
All right. So yeah, if there's any more question, can just post it in Discord. Yeah. Cool. So yeah, we do have a talk scheduled for next week, right, Kishore?
Yeah. So I will share. So like I think next week Shaozen Fu is speaking, and then
Okay.
after that I think Hayata Yamasaki will speak, and then I think someone from Japan, and then I think someone from Korea. So I think the different talks about it and all that. So I will share the details. Yeah.
Awesome. Sounds great.
Yeah.
All right. Cool.
Yeah.
So yeah, thanks everyone, and thanks Kishore. So see you guys next week.